Okay, one of the things that I find students struggle with initially when we're talking about elements and compounds and mixtures is that when you guys are new to chemistry, you don't really know your periodic table all that well. Like if I were to give you the name molybdenum, do you think that's an element or did I just make up a word? Exactly, right? Molybdenum is actually an element. It's MO, I believe. It's number 42? 42? But like at first, students sometimes struggle because they're like, is that really an element or did you just make up a word? If I went to blah, 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 that was probably made up, right? So at first, students really struggle with knowing what are elements, what are compounds, what are mixtures. My hope, though, is that you're becoming more familiar with elements because you have a periodic table in front of you. The more you read through it, the more you go, okay, yeah, I recognize nitrogen, I heard that one before. I recognize helium, I heard that one before. Right? And the more you do it, the better you get, which again is another reason why it's so important to do labs and assignments, because it helps build familiarity with the periodic table so you know what the heck you're talking about. Well, today and tomorrow, I really want to focus on compounds. Because again, sometimes I find kids have that same problem where they're not really sure whether it's a compound. Let me give you an example. Is dirt a compound? Actually, dirt's a mixture. Because dirt is made up of things like carbon dioxide and sulfur dioxides and nitrogen trioxides. And so what we need to know now are like what are the actual compounds. So I want to begin. My video from chemistry just finished. Where do I need to go? I want to begin by reminding you guys of what the definition of a compound actually is. Does anybody actually know off the top of their head what the definition of a compound is? Two or more elements combined together, and sometimes you might say in a fixed ratio. Ever heard that before? A compound is two or more elements combined in a fixed ratio. So let me go back to dirt. Dirt. What elements? Yeah, dirt's more of a mixture because there's not elements in dirt. But let me give you a different one right here. What if I gave you the element or the compound of water? Maybe you've heard before. Water has a formula, H2O. The reason why this is a compound, make sure everyone's with me, guys. Give me full attention here. Is that you've got some H's. H's are hydrogens. You've also got some oxygens. And they're in a fixed ratio because this 2 right here means that you have 2 hydrogens, and this oxygen right here, since we don't have a number written beside it, means there's only one of them. That's a good example of a compound. Let me show you another compound. CO2. Anybody know what CO2 is? Carbon dioxide, yeah. And it's got similar concepts to it because it's one carbon, because we only have one C written, and then oxygen, there's a 2, so you have 2 of them. And hopefully the numbers actually make sense, because it would be really ridiculous to write HHO or to write COO, because like it gets a little cumbersome when we start talking about a compound like C6H12O6. C6H12O6 is basically sugar, but if I had to literally write out what it was, it would be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 7, 8, 9, 10, 11, 12, 1, 2, 3, 4, 5. Okay, that's ridiculous, right? Every time that I want to talk about glucose, I would not want to do that. But this is what a compound is. A compound is where you take lots of elements, put them together, but with fixed ratios, meaning that we're going to put some numbers down here in the corners that tell us how many of them we need. Well, let's say we talk about dirt. Does that mean you have one D, one I, one U, one T?
Dirt is
yeah, so it doesn't fit in that same way, right? So we're talking about things that have chemical formulas, but it's not by itself. If I were to give you N all by itself, that's nitrogen, it's an element. If I were to give you Cu by itself, that's copper. That's an element. And the more you use your periodic table, the better you get at it. But if I were to give you copper and oxygen together, now we're talking a compound. Does that make sense? So that's what we're going to do over the next couple of days, is focus on compounds. And we're actually going to have 2 lessons. One is going to be on things called molecular compounds, and then tomorrow we're going to talk about things called ionic compounds. We're going to do them like half each day. Because there's actually 2 different ways that compounds can be formed. There's actually more than that, but we focus on 2. And I need to remind you guys of some terminology we've used in the past. The terms of nonmetals, versus metals. Quick aside. Where do we find the metals on the periodic table? What separates them? The staircase. I'm going to find a periodic table here real quick. Give me a sec. Oh, actually, this will work right here. I know this isn't exactly the periodic table, but hopefully you guys recall that there's a little staircase we draw right here. And it helps separate what we call the metals from the non-metals. Okay, which actually that helps answer this question right here. You guys all with me? Now, there's two ways that compounds can form that we're going to talk about. One of the ways is that you have two different non-metals joining together. I'll give you an example of that. Carbon dioxide. Carbon is not a metal. It's on the non-metal side. And oxygen is also a non-metal. So this is one way that a compound can form, carbon dioxide. Where if you know your periodic table, I'm just going to draw just a basic one that looks like this. Carbon's been about here, oxygen is over here. They're both on the non-metal side. So the words we give that are, we either call it a molecular compound, or you might hear the word covalent compound. Can I give you guys a piece of advice? Rather than having me make you write down notes, that's why I give you them in advance, I want them already here. One thing that would be useful then is maybe write the definition of this down on your formula sheet. All right? That way next time I assess you on it, if you don't know the definition, it's on your cheat sheet. Does that make sense? That's a good learning strategy. So, I mean, you don't have to, but a molecular compound involves two different non-metallic elements. Now, the other thing we're going to learn about tomorrow, I'm just introducing it today, is where you have one thing that's a metal and one that's a non-metal. And a great example of that would be sodium and chlorine together. Anybody know what NaCl is? Salt. Yeah. And if you know your periodic table, and hopefully you're learning it, sodium is found over here, chlorine is over here. Here you have one thing on this side and one on that side. So those are the two main naming schemes we're going to have. One is where you have two non-metals combining together, like carbon dioxide. Or one is where you have something on this side of the table and something on this side of the table. And they bond differently, so we have to have a lesson for each one. So why don't we start talking about just, in general, what we've led up to here. Okay? We've been focusing on matter and mixtures and stuff. Today, we're going to focus very specifically, though, on the idea of compounds. And if we want to add to this chart, we can almost take this chart and we can break it up into like a further flow chart. Because today we're going to talk about what we call the covalence. And then tomorrow we'll talk about what we call the ionics. So like in a way, we could just keep this chart going and kind of break it down further. Does that make sense so far? Okay, so let's talk a bit about elements though before we get to compounds, because what do compounds get made up of? Elements. So before I focus a little more on compounds though, let's talk about the basic building blocks elements again. Okay? Here's a word that I need you guys to know. It's called an allotrope. Allotrope. It sounds like a dinosaur. Allosaurus, allotrope, I don't know. An allotrope. These are what are known as like the possible naturally existing form of elements. How am I going to describe this here? Has anybody ever seen that this is oxygen? O stands for oxygen. But oxygens never come by themselves. Oxygens always come in groups of two. And I write it as O2, oxygen gas. Has anybody ever seen oxygen written like this before? No. Okay. Okay. There are a lot of elements out there that, when they're in their elemental form, they don't come by themselves. They come in groupings. Most things are found in groups of one. And so it's usually best if you just write down on your periodic table which ones are the exceptions. For example, if you were to just have copper by itself, copper comes in a group of one. But rather than writing a one, we just leave it blank. Nickel comes in a group of one. Almost everything by itself comes in ones. But there are some elements that, for whatever reason, they're never by themselves. They come in groupings. Let me show you some examples. Mercury, for example. Mercury actually comes in groups of two. You never find mercury by itself as a single one. It's like it's always got a buddy. And so here's some other ones I might want to recommend. If you have your periodic table, add them to the table. Okay? So they are hydrogen, nitrogen, oxygen, fluorine, bromine, and iodide. those ones there, they always come in groups of two. We have a special name for them. We call them diatomic. So if you were to ever ask me about elemental nitrogen is not N. It's N2. And at first you just need to just memorize them. So I would say write them down. So on your periodic table, what I often suggest for kids to do is find some of the ones I have on the list here, and go find, like, say, mercury, which is right here, and just put a little 2 next to it so that you know that if you're ever writing it by itself, you need 2 of them. Has anybody ever heard of ozone? Ever heard of the ozone layer? Yeah, there's an ozone layer around our Earth that helps shield us from some of the sun's damaging rays. I want to show you 2 different allotropes of oxygen. If you have O2, that's oxygen gas that we breathe. That's O2. But oxygen can actually form another allotrope. Oxygen can also go in groups of 3. If you ever have 3 oxygens, it makes what's called an ozone. And it actually makes a ring. What ends up happening is oxygen binds together in a little triangle, which is kind of cool. So what I need you to be aware of is that if you're writing an element by itself, we don't usually write a 1 afterwards if there's only one. But there are many things that come in different groupings. I need you to be aware of those groupings. So here are some other ones you should know about. Sulfur actually comes in groups of 8. We actually call them flowers of sulfur. And I believe the reason why we call them flowers of sulfur is that, you know how like a flower has petals on it? And there might be, like, say, 8 petals around the flower. I think that's the reason why we call them flowers of sulfur, is because there's 8 sulfurs all together in like a flower shape. Phosphorus is never found by itself. Phosphorus always needs 4 buddies together. And arsenic needs 4 buddies. So I want to try a little task here just to make sure you guys are clear on things. Let's say I asked you about the element of tin. Does it need a buddy? Does anyone actually know what tin's formula is? See if you can find tin on your periodic table. It's SN, and it's number 50? So here's my question. Should you write a number after tin? And unless I've told you about one of these allotropes, no, don't worry about it. So if it's not on this page right here, don't worry about it. You're just going to have one tin by itself. But what we would do is we would say that tin is solid, because tin is like, it's one of the black elements in the periodic table, so it's solid. We'll try another example here. What if I were to ask you about chlorine? Can you guys find chlorine on your periodic table? It's number 17. Now, does chlorine come by itself or in a group? And really, the only way you know is if you have the slide written down. And I missed writing chlorine on the slide. Chlorine is actually an diatomic gas. It's a good thing we did this one. Can you add one more to the list? Chlorine actually does come in groups of 2. So whenever you write a chlorine, never write it by itself. Have it come in like a package of 2. What is that 2-pack? Yeah, like all of these ones here, if it ever comes in a group of 2, and there's a lot of them, we call them diatomics. Di because there's 2, that's the prefix 2. Now, what state of matter is chlorine? If you look on the big periodic table at the back, chlorine is number 17. It's Cl. It's way on the far right-hand side. It's red. So that now tells us to put a gas state of matter afterwards. Let me try a few more examples here. I want to make sure you guys are all clear on this concept, because if we can't work with elements first, it's really hard to do compounds next. So let me pick another one. Can you guys find calcium? So you can find calcium on your periodic table. It's number 20. And again, the more you do it, the faster you get. Everybody find number 20? Okay. Let's do state of matter first. What state of matter is calcium? On your tables here, it's yellow, right? Yellow means that it's a solid. Now the other question though is, does calcium need to come with buddies or not? That's what an allotrope is. An allotrope is, does it come in groups of 1, or in groups of 2, or in groups of 3, or 4, or 5? And again, unless it's written on the slide here, it just comes in groups of 1. So you might notice that I don't see calcium written anywhere on here, so it's in groups of 1. what if I were to ask you about phosphorus? Phosphorus, if you can find it, is number 15 on your periodic table. So first, let's talk about state of matter. What state of matter does phosphorus come in? What color is phosphorus? Phosphorus is green, but according to the green, it's a non-atomic solid, so I'd still call it a solid. But the other question you have to ask yourself is, by itself, does phosphorus need buddies? Okay, that's the best way of thinking about this. There are certain elements that are totally okay with being by themselves when they're elements, but there are other ones that they need to have other buddies with them. So all you got to do is just look at the little chart I gave you here and see what does phosphorus come in groups of? 4. So every time you write phosphorus by itself as an element, make sure you always write P4. And if you ever write sulfur, write 8 of them. If you ever write oxygen, oxygen can actually be in 2s or 3s, actually. Does anybody have any questions about that? What do these little numbers down here then mean? Well, it tells you how many of them there are. If you have a nitrogen 2, it means that this nitrogen bonds to another nitrogen. If you have a chlorine 2, it means that this chlorine bonds to another chlorine. But if you have SN all by itself, it means that it doesn't need to bond with a buddy. It can just be in a group of 1. So that's the first thing I need you guys to be aware of. And the reason I point that out is that these numbers down here are really important. These numbers tell you how many of something you have. And that's very important when we start talking about compounds, because as I've already shown you before, where's a blank slide here? If I were to give you CO2, is this an element anymore? No. It's not an element because you have carbons and you have oxygens. But these numbers down here in the corner, they tell you how many of each thing you have. In a carbon dioxide, you have 1 carbon, and then you have 2 oxygens. That's what a carbon dioxide looks like. It's magical. If I were to give you CH4, what is it made up of? Well, it means you need 1 carbon, and you need 1, 2, 3, 4 hydrogens. And maybe you guys have seen pictures of modeling kits where you use this could be like a molecule like this, where you kind of draw like balls and sticks. And we'll get to that eventually. But the concept I want you guys to get right now is that these numbers down here in the corner, they're not just for show. Like they're very important because it tells you how much of something you need. So, one last time on this slide here. If you don't write this down in your periodic table, you really, really, really should, because a lot of times people just need to memorize these, but this is like your first month of chemistry. I don't expect you to have this memorized. So please, please, please write it down so that you know that you never write H by itself. You never write H by itself. H always comes in packages of 2. That's actually an analogy I use sometimes. You know how sometimes you go to the store and you buy, say, like 1 toothbrush, but then there's like the value pack where you get 2 toothbrushes in the same package? Well, or maybe for the price of 1, right? But you can buy like 2 in a package, right? Or maybe I go and I buy like a 4-pack or something. Elements work the same way. Some elements are bought individually. You just need 1 of them. But some elements, you can't buy them individually. You have to buy a 2-pack or a 4-pack or an 8-pack. Okay, so if you don't write these ones down, you'd never know. So far, so good? Okay, I want to talk about carbon for a bit, because carbon is very unique in terms of allotropes. Here are some different examples of carbon that I think you guys are familiar with, at least 3 out of the 4. This right here, off on the side right here, is actually carbon as like soot that would be left over after you like burn something, right? Just like the black ashes that are left over. This would be a good example of carbon in a group of 1. And so usually when it's in a group of 1, we don't actually write a number next to it. But carbon can actually form a lot of different allotropes. Carbon can actually be used to make pencil lead, which we call graphite. And I don't recall exactly which allotrope it is, but I want to think that this is carbon 4, because I believe carbon can come together in groups of 4. In this example right here, it's just a dust. But if it comes together in groups of 4, it's graphite. Girls, can I get your full attention, please? I don't know if you guys are aware of this, but diamond is actually pure carbon as well. when you guys are using pencil lead in your pencil, it's actually the exact same element as a diamond is. Except this allotrope, I believe, is like carbon in groups of 20. I don't know that that's for sure the number. I need to go Google those again. I don't have them all memorized. But like this one right here, carbon in groups of 1 is not valuable, right? Soot, who cares? But if it comes in, say, a 4-pack, well, now it's pencil lead. That's a little more valuable. What if it comes in a 20-pack? Well, now it's diamond. Carbon's actually really cool. Carbon can actually make this molecule here called a fullerene, which honestly looks like a soccer ball. It's super cool. This one right here, I believe, is a carbon in a group of 40. So hopefully I've made my point, because I've been really redundant right now. But I need you guys to be aware that in elements and in compounds, you don't always have things one at a time. Sometimes you have 2 or 3 or 5, or in the case of this one right here, you might even have 40. Cool new stuff in the science world involves making carbon nanotubes. You've never heard that phrase, carbon nanotubes. They get used in all sorts of techie type stuff. And it involves them basically adding more and more carbon together in a tube format. It basically means you'd have a carbon here, 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 and here. You kind of make a ring out of it. And then you have another one here, 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 and here. You make another ring out of it, and then you start to attach it together. And you make like a long tube that works like this. It's almost like there's like an opening on one side, and they keep going. I'm not a good artist. I don't think I done a good job of explaining. But long story short is they can actually start putting together like 100 carbons together in a row and make something cool out of it. So, have I made my point though that this number down here you need to really pay attention to because it tells you how many you have? Cool. Let's move on. Well, what if you're talking about a compound? Well, that same logic still applies. I want to show you some examples of compounds. Here's NaCl. If I give you NaCl, how many of each do you have? And hopefully it's pretty clear now that I've really, really beaten this to death. There's not a number written next to the sodium, and there's not a number written next to the chlorine. So you just have one of each. You have one sodium and one chlorine. But here's another compound, CCO3. Hopefully this is clear. There's not a number written next to Ca, so there's one of them. There's not a number written next to carbon, so there's one of them. Let's say there's a little 3 here next to oxygen. You need 3 oxygens. So this molecule, if we were to kind of draw it, might look something like this. You have a calcium, which attaches to a carbon. And then the carbon attaches to 1, 2, 3 oxygens. Right? And this might be like how the molecule looks. Now, we're not going to do drawings in this course. Like, we can get there eventually, but this would be like kind of what the molecular shape looks like. One more example here. Al2S3, the 2 means you need 2 aluminums and you need 3 sulfurs. So a question I might ask you then is, how many elements are used to make this compound? How many elements are used to make this compound? And you'd say, well, there's 2. Right? There's 2 elements. You need some aluminum, some sulfur. But if I were to ask you how many atoms are there, you'd say 5. Because you have 2 of these plus 3 of these. So I might say that you need 5 atoms in order to make this compound. It's made up of 5 of them. 3 of one and 2 of another. Any questions? Okay, well the main focal point of my lesson then is I need to teach you how to name things. Every compound has what's known as a chemical formula. And right here, these things right here are our chemical formulas. And so I need to show you how to name more compounds because my guess is you probably only know a few. CO2 is carbon dioxide. H2O is water. Maybe you know CH4 is methane, but I need to show you how to name some of these things. So, I got some pictures though I just want to use to illustrate my point again, but hopefully you guys get this. This NaCl right here is really made up of 1 Na and 1 Cl. What would I name this molecule right here? Yeah, because there's 2 hydrogens and 1 oxygen. Yeah, you guys know it's water. Here's another slide just kind of showing the same thing, but I think I made my point, so I'm going to move on. I'm going to come back to the slide. Actually, let me do it now. You know how we had 2 different names we were going to learn today? One was known as covalent and molecular. This is what we're going to do today. And then tomorrow, we're going to talk about ionic compounds. Is that how you spell tomorrow? 2 M's, 2 R's?
No, one has no choice.
Anyways, tomorrow we're going to talk about ionics, and it's a little more challenging because there's actually 3 different subgroups of ionics. So I'm going to use this flow chart more tomorrow, but today all we're going to do is talk about how to name covalent stuff. Were you looking for something? Other one. Okay, so let's talk about.
You already give him a lecture?
Yeah, I heard it loud across the hall too. But
Talk about
late work. Do you want to just do it now?
Well, you just gotta get it done, guys. You're almost in high school.
I actually like to tell them that they are in high school.
Yeah.
Pretty nice.
This is your transition year. You're going from little baby, middle school, adolescent kid to young adults. And Mr. Schultz can tell you, we've already dropped kids down from math because they're not doing it in high school. And some of you, it's been everyday using has been on there. Trying to get it done. The nice thing, though, I will say, is that the majority of the kids who went there today for interventions, the majority got their work done. So you have been working on it and got some of it done. So that was good to see. But some of you just need to step it up, get off your phones and.
Yeah, I mean, we have flex block for most people. If you're in band, you have that first period block. But I mean, the reality, guys, if you have homework, right? When you're gonna take streams in high school, you've got work you have to do at home sometimes. This is the reality of getting into high school. Sometimes you'll get done all at school if you work really hard. But okay, let's talk more covalent bonds because I don't want to lecture you guys. You guys know what you need to do. You just need to do it. So here's how it works. Covalent bonds, like I already said before, are when you have non-metals bonding together. So to keep things simple today, you know how you have your whole periodic table? I don't actually want you to rip it in half. But literally all we need to do is just rip off just one section of it. If you have like your table that looks kind of like this, which has a little gap in the middle, and there's the staircase line right here, all we're going to focus on is just this section right here today, just to keep things simple. So there's only a few elements we need to be aware of. Boron, carbon, nitrogen, oxygen, fluorine, neon, silicon, phosphorus, sulfur, chromium, argon. Can you guys find what I'm talking about here? Only be looking here today, just to keep it simple. Okay. And the way this works here is that these elements are going to share their electrons in their energy levels. And I want to do a recap on this. So this is one of the reasons why we learned about our scientists before is because we actually need to know how energy levels work. So we go back to Rutherford. Rutherford had this great experiment.
Chandler Medicine Crane, please go to math class.
Rutherford had this great experiment where he discovered that all of the protons and the neutrons were in the nucleus, and that electrons were orbiting around because of that gold foil experiment. And he had a name. He called these things orbitals. And he named them orbitals because they were literally going in circles around the nucleus is what he thought. But we actually know that's not correct. The new term we like to use, because they don't actually orbit, is we call them energy levels. And what ends up happening is all elements will have electrons hopping back and forth between these energy levels. Does that make sense? How many energy levels are there? 7. Why? Why are there only 7 energy levels? The periods, yeah, periods going across. Each one is known as an energy level. Okay. So if you guys could take a periodic table. I wish I had one nearby here. Can you guys find where helium is?
Here.
Helium is number 2. Helium has 2 electrons in 1 energy level. That makes sense? It's in the first row, has 2 electrons in 1 energy level. Now find neon. Neon is right below it. It's number 10. It then has 10 electrons, but it doesn't just have 1 energy level, it actually has 2 energy levels because it's in the second row. And one of the cool things about all of those ones that are in the very, very last column, we gave them a name, we called them noble gases. Do you remember why we called them noble gases?
Oh, yeah.
Go for it.
Because they don't mix with anything else.
Yeah, they don't mix with anything else. They don't like to react. And here's the reason why. Everything that on the periodic table is in the far right-hand column has what's known as a full energy level. All of its energy levels are filled up with electrons. It has no room to add more electrons or get rid of electrons. And so it's considered very stable. So I know I don't have a periodic table nearby here, but everybody that would have been in this back column right here, we call those the noble gases because they don't react. They have what's considered a full energy level. So you know how I was telling you that we're only going to focus on a few elements over here? Well, we can even cross a few off our list because helium, neon, argon, krypton, xenon, and radon, they actually never react because they're considered full. So we actually only need to focus on the remaining ones. And what ends up happening is these guys don't have what's considered to be a full energy level. They don't quite have all the electrons that are possible to be filled up. And so what they're going to do is they're going to share electrons with other compounds and form bonds. And so a key word I need you guys to know here is this one here. They share electrons. And the sharing of the electrons creates the bond. Give me some examples. I'm going to skip ahead a slide here. Can you guys find the slide right here? I know that I'm going out of order. Can you find the slide here? Here's how we name these things. A compound usually has two parts to it, right? Like CO2, H2O, SO3. So when you see a compound, here's how you name it. You look at the first element you see, and you just write out its name. So in this one right here, C stands for carbon, so you call it carbon. Then the second thing that you have to figure out how many you have. You see how there's a little 2 down here in the corner? Well, the prefix for 2 is the word di. Di is for 2. Tri, as in tricycle, is for 3. Tetra, like a Tetra Pak, is for 4. Penta, like a pentagon, 5. And so everything has its own little prefix. So we call it carbon dioxide because carbon you just need 1 of, and then this di right here means you need 2 oxygens. However, we don't actually say oxygen. The second word, we always change the ending so that it ends with the letters IDE. Particularly all these ones right here. See how it all ends in "ide"? You always change the ending to something "ide". So we don't call it an oxygen anymore, we call it an oxide. We don't call it a fluorine anymore, we call it a fluoride. So maybe you can kind of piece together how this naming scheme works here. See how there were 2 nitrogens right here? Right? Because N has a 2 afterwards. Well, 2, the prefix for 2 is di. So you call it a dinitrogen. But how many oxygens do you have here if we don't write a number afterwards? We just have 1. So we would then use the prefix for 1, and that's mono. Mono is meaning 1 by itself. So you call this dinitrogen monoxide. Because you have 2 nitrogens, and you have 1 oxygen. Mono is kind of a tricky one. We only use the word mono in the second word. Okay? See how there was only 1 carbon right here? You never write monocarbon. We never start with mono. If we don't use a prefix, we assume there's only 1. Okay? But we can use that in the second word. So, like right here, phosphorus pentafluoride. Since I didn't write mono or anything in front, it just implies you need 1 of them. And then pentagon, means you need 5 of something. And so this actually helps you now start understanding how some naming schemes work for compounds. So I want to go back here, if I could, to this slide right here. This is the one I skipped. Here's some rules on how to name things. And if I could, again, give some advice, put some on a periodic table. Find some space in a corner somewhere and write down the basic way that you name things. So here's how it works. You need a prefix, and then you write the first element, and then you have a prefix, and you write the second element, but the ending of the word changes to "ide". And that's how you name covalent compounds, which is where carbon dioxide comes from. Carbon, you want 1 of them. Oxide, you want oxygen, but the dioxide means you need 2 of them. Another piece of advice I'm going to give you. I got to give a second for you to write this down. In order to be able to do this, then you need to know what all of these like prefixes are. So like di is 2, tri is 3, tetra is 4, penta is 5. So again, write these down somewhere. That's actually what I have on the next slide is a list of all of the different prefixes that you might use. Here's a list. If you have 1 of something, you call it mono. 2, call it di. 3, call it tri. So what I often suggest to kids to do here as well is make a chart somewhere on your table, because you're new at chemistry. Right? And when you're new at things at first, it takes a little while for you to become familiar with it. So I'm not just encouraging you, like I'm really, literally, guys, I'm telling you, you should do this. Right? Write these down, because eventually you'll memorize them. But until you get to that point, put them on your periodic table. Just in case you need to have 8 of something, and you're like, what's an 8? 8 is octa. That makes sense. Octopus, octagon. Right? But I mean, there's some that you're not as familiar with, like say hepta, maybe nona for 9. So take a second to write these ones all down. And then we're going to do some examples. We're going to try to name some compounds now. If you don't finish your list, by the way, this is in your notes, right? So just go back and get it later. So let's try some examples. So if you can find this next slide here, we're going to try to name some of these. And many of these you might have heard of. Like the very first one, CO2. You probably know it's carbon dioxide, but let's just review why. There's not a little 1 written here in the corner, but it implies that there's 1 because there's only 1 written. Which means the prefix for 1 is mono. But we never start over with mono. If there's only 1, we just start with the word. So C stands for carbon. So we start there. Then for the next compound, we got to look and see how many of them there are. And see how there's a 2 in the corner? There's 2 oxygens. The prefix for 2 is di. And then for the last part, di what? What did you have 2 of? Well, you had 2 oxygens. But we don't call it carbon dioxygen. We call it carbon dioxide. Yeah, just make sure you always change the ending to "ide." Just a common thing we do. That makes sense? Let's try the next one. Okay, first element you see in the compound is carbon. So, okay, we'll write carbon again. How many of those carbons do we have? 1. Which means it should have been mono, but we don't ever start a word with mono. That's just an exception to the rule we have. Wait, then look at the next thing we have. Hey, it's oxygen again. But how many oxygens do we have now? Okay, but this time we do need to write mono. So we would call it mono. And then, what do we have 1 of? Well, we have oxygen. So we call it carbon monoxide. You guys ever heard of carbon monoxide?
Yeah.
It's actually quite a dangerous thing to breathe. Yeah, it actually will suffocate you. You need to breathe in oxygen, and if you're breathing in too much carbon monoxide, maybe you have like a carbon monoxide detector in your home. Maybe you've seen those before. Like they're actually quite important, so people don't. Like if you have a fireplace, for example, and it leaks carbon monoxide, it's actually very dangerous. Okay. Let's try one more here. N3. Now this one actually starts with not just 1 of something, so we have to put the right prefix. So, what's the prefix for 3 of something? Tri. So we're going to start with this. We're going to call it a tri, and then N is nitrogen. So we need trinitrogen. And then the next thing we have is 6 of something. We have 6 hydrogens, but what's the prefix of 6? 6 was a hexa. Yeah. So we need a hexa, and then it was supposed to be hydrogen. But we have to change that to hydride. That's how it changes it to. So you would call it a trinitrogen, because there's 3 nitrogens. Hexa, hydride, because there's 6 hydrogens. Does that make sense? Any questions? This is the sort of thing where, if I want to give you guys some advice again, I give you that silly story about Ryan Kessler working on his wrist shot yesterday, right? When it comes to studying for tests, be like Kessler, at least in terms of his wrist shot. Work on stuff that you know you're struggling with. And so if this made sense to you and you're like, I get it, don't practice it. Work on something else. But if this is something where you're like, whoa, I don't think I get that, Mr. Schalk, then ask me for help. I will find you practice, right? And just like Kessler did, where he shot 1,000 pucks a day, I can find you a couple of worksheets so you can practice it so you get better at it. Because really, that's how you get better, right? You just do repetition. One thing you guys need to know about me is I'm not the kind of teacher who gives you a lot of worksheets. Okay? I give you a lot of stuff to do, but I'm not a worksheet teacher. I'm not going to say, here's a worksheet that has questions 1 to 50 and just name all this stuff. If you want that stuff, I'll find it for you, but I really believe in more of a targeted approach. You might need to work on this, but you might need to work on that, and you might need to work on this. And so I really want to encourage you guys to figure out, like, if you need more practice on this, because this was like you lost me, Chris, then, you know what I'm saying here? Then focus on it. But if you get it, let's work on something else. So let's try the other way here. What if I gave you a written name? Could you write out its formula? So let's try it here. Silicon was written all by itself. So we just need to know what silicon's symbol is. If you can find it on the table, again, the more you do it, the more better you get. So you do need some practice. But silicon is Si. Then you see tetra. Tetra means you need 4. Well, what do you need 4 of? 4 fluorides. Okay, well, what was a fluoride from? Probably from a fluorine. Fluorine is F, so we'll need 4 Fs. So silicon is there. Tetra means the number 4, and then fluoride means the F. There. Now you know we're a new compound. Silicon tetrafluoride. Once you get the hang of this, I find there's some kids that literally need to do it like 10 times, and they're like, I got it. But there's some kids where they need to do it like 50 times, right? Just to help build it in, right? Everyone's got different ability levels. My hope is just to help you guys improve. Okay, tetraphosphorus. Phosphorus is a P. And you guys can see this one ends in oxide. Oxide is from an oxygen. So you need P's and O's. Tetra means you need 4 of them. Deca means you need 10 of them. This is a really weird compound. It comes in 4 phosphoruses and 10 oxygens. You guys think you can replicate this kind of on your own? Like after I show you a few examples, do you kind of pick up on the idea? Let's try one more. Dinitrogen monoxide. What's a nitrogen? N. What's an oxide? O. No. Well, hang on a sec. We need to think of those numbers. Those numbers really make a difference. Because dinitrogen means we need 2 nitrogens. Monoxide means we just need the 1. And I got to tell you, those numbers make a huge difference. Because I want to show you a bunch of other nitrogen-oxygen compounds. This is not the same as this, which is not the same as this, which is not the same as this one. Those are 4 compounds I can think of off the top of my head that all involve nitrogen and oxygen. And they are all vastly different. Some of them we breathe. One of them is laughing gas. I forget which one it is, but one of those ones is laughing gas. One of them is the gas that a dentist might use to knock you out when you have to get like cavities and you go under sedation. You know what I mean? And so they have very, very different properties. So you don't want to mix up your carbon dioxide with your carbon monoxide because they aren't the same thing. So make sure that you are paying really close attention to the little numbers that go in the corners there because it totally changes the compound. That make sense? Okay. Well, I mean, that's basically the concept. The question now for you guys is, how much do you feel like you need to practice it? If you think you got the hang of it, we might only need to do a couple of examples here. I'm going to skip over the slides here. I don't have a slide in my notes of extra examples, do I? Usually I throw a whole bunch more in. I just have more stuff to read here. Okay. I will say this. You guys have you guys got your textbooks? Yeah, I see a bunch of them around the room. I don't use textbooks a ton, but if what we just did right here, if you feel like as we look at this and you're like, I got it, move on. Right? But if you feel like you're really struggling and you're like, I need practice, I need you guys to be able to, as learners, be able to admit when you get something and when you don't. If you don't get it, please ask. I hope I'm not a scary person to talk to. Okay? Because you're probably going to be in my room for like the next 4 years.
Don't
take
worry,
any maths or sciences.
You're not that scared.
Good.
You're terrified.
I need you guys to be able to ask me for help when you need it, right? Because that's why I have a job. So if this didn't make sense to you, ask me, I'll get you help. Okay, last thing, then we're going to call it a day. I want you guys to know a couple of properties of molecular compounds. So again, molecular compounds are when you only have non-metals combining with each other. So it's only a small section of the periodic table that does this. And here are some things we know about them. They all have very low melting points and very weak crystals. I'm going to talk about that for a second here. Here's an example of some of the compounds that you guys might have worked with so far that are all molecular. Carbon dioxide. What phase of matter is carbon dioxide? Solid, liquid, or gas? It's a gas. Anybody know what phase of matter carbon monoxide is? Actually, it's also a gas. What phase of matter is water? Usually it's a liquid, but is it actually hard to turn water into a gas? We boil it all the time, right? We boil water. Here's the point I want to make. Nearly all covalently, guys, stay with me, please. Nearly all covalently bonded molecules have a low melting point. Because what happens when you melt something? You go from a solid to a liquid. What I mean by this is almost all molecular compounds are either a liquid or a gas because they've already melted. You rarely come across carbon dioxide as a solid. You rarely come across nitrogen dioxide, laughing gas, as a solid. Another thing I need you guys to know is they have very weak crystals. They break very easily if you do make crystals out of them. We don't usually make crystals out of carbon dioxide or carbon monoxide, but it's very easy to make crystals out of water. How do you make crystals out of, guys, can you please focus? We're almost done, I promise. How do you make crystals out of water? You freeze it. This happens all the time in the wintertime, and I hate it because water freezes to my windshield as frost. But here's the good news. It's actually not that hard to break the crystals of ice on your windshield. All you need is the scraper tool, and you can literally scrape them away. And so their crystals are actually very weak. I mean, I know it's annoying to have to scrape your windshield, but relatively, that frost, the water vapor that turns into ice on your windshield, you can actually scrape it pretty easily. So you actually do have weak crystals. Here's a chart that I want to use to show you just some melting points of these things I found. Most of them actually have very, very, very low melting points. Carbon dioxide, it doesn't even have one that we can find. And most of these ones are like either 0 or in the negative numbers, which means almost all covalent molecules are liquids or gases, but there's a couple of exceptions. This one right here, sugar, is actually a solid. And you'll notice the sugar, though, there's one unique thing about it here, though. It actually has 3 different pieces to it. See how there's carbon, hydrogen, and oxygen? And the numbers are big. You have 12 and 22 and 11. We don't even have prefixes that go that big. And so the only reason why this one's a solid is because it's a really big molecule. But in general, these things have very low melting points. Here's another thing about them. We'll test this in a lab another day, but they actually don't conduct electricity. These things don't have the ability to conduct. Remember how I took that little tool with the 2 little prongs on it, and I pressed the button to see whether it conducted? These things here shouldn't conduct electricity. I think I'm going to leave these slides here, and I'm going to start with those tomorrow. Because I think I'll leave it here for right now. This last slide right here is kind of my transition to tomorrow. We've now talked about how covalent compounds work. And covalent compounds involve sharing electrons between 2 things that are non-metals. Tomorrow I'm going to show you another naming scheme about things where one of them is a metal and one of which is a non-metal. And you know that little flow chart I kind of showed you briefly there? We're going to work on the other half of the flow chart tomorrow. And these guys bond differently. These guys share electrons. These guys transfer electrons. Okay, last thing. While you got your periodic tables out, there are actually some compounds that actually have a formal name. Water, H2O, is actually a common name for it. We should actually call it something different. Water should actually be known as dihydrogen monoxide. Have you ever heard that for water? Water is actually dihydrogen monoxide. 2 hydrogens, 1 oxygen. That's oxide, by the way, monoxide. So there are some compounds that rather than calling them their formal names, we actually give them give them a different name. So like water is one. H2O is water. This one right here, we should actually call it carbon tetrahydride. Right? One carbon, tetra, 4 hydrogens. But sometimes these chemicals, it's better just to give them a different name because it's a mouthful to say these sometimes. So we call it methane. Have you ever heard of methane? It's actually what we use to heat our houses. Like it's natural gas is what methane is. So here are a couple of examples of compounds that I think might come up in the first couple of years of you guys learning chemistry. It wouldn't hurt to write these down as well. Because although, like you could call this nitrogen trihydride, dicarbon hexahydride, we have other names we give them. Okay, that's my lesson. So what we talked a lot about today is, can we now start to name our compounds and know the proportions that come in, like the ratios, the 2s and the 3s, the di's and the tris. Okay. Here's what I recommend you guys do. If you're behind on stuff, I'm tired of giving lectures. Can you please start working on finishing up old stuff? It's late, it has to count for marks. Okay? Do a good job of it. But moving forward, we have some new things to do as well. We're going to do a new lab next week. Okay? There's also a new assignment posted. You can start looking at that new assignment to work on. Okay? If you want to, I can find you practice on how to name some of these things. If you're like, whoa, I don't think I got the idea down, I'll find you textbook questions to practice. Okay? I say this at all the end of my classes. You guys are going to learn something. We have about 10 minutes left over. Do something. Okay? Do something productive. You've got 10 minutes. Please don't pack up. That's such a waste of time. Okay? Find something that's productive. Do questions 1 on the assignment, and then call it a day. Okay? But don't waste time. I'm going to give you time to work on whatever you want to work on. Use the time well, okay? Call me over. Ask questions as you need. Get help.